Welcome, everybody. We're going to get started here in just a couple minutes, but I'll give some time for everybody to kind of come in and join. All right, I'm going to go ahead and get started just because there's actually a whole lot of content in this webinar, and I want to make sure that we have time to get through as much of it as possible. So welcome. Thanks, everybody, for joining us here. My name is Chris. I'm going to be your host for today's webinar. I'm also one of the co-founders of MassDriver, which is a visual internal development platform that enables engineers and developers to deploy production-ready infrastructure and applications in minutes. We have other members of the MassDriver team in the chat and Q&A, so they'll be answering any questions that you have, and we'll try to address them on air. This webinar is also being recorded and is going to be uploaded to our YouTube channel. And I believe it's also streaming to Twitch and these other platforms, so it'll be available there as well. Today, we're going to be investigating, diagnosing, and fixing some of the common issues that will arise when you're running applications in Kubernetes. If you'd like to follow along and debug these applications with me, I'm going to post some links into the chat here. So let me get them in first. Right here. So that first one right there is going to be a link to the repository that we're going to be using to go through all of this. This next one is going to be kubectl, which we'll talk about here in just a moment. It's the Kubernetes CLI tool. And the last one that I'm linking here is Helm installation instructions. Helm is a package manager, which again we'll be talking about momentarily, but this is how we're going to be deploying the applications into the clusters using Helm. Make sure you download kubectl and Helm before we get started. You got probably a few minutes here before we actually get in and start debugging. This is intended to kind of be a workshop that you guys can follow along with. However, if you don't already have a Kubernetes cluster up, you probably won't be able to get one up in time, and I would just watch and you can follow along with the recording. If you don't have a Kubernetes cluster, I'm going to recommend you head to massdriver.cloud. We can help you deploy a production-ready Kubernetes cluster in AWS, GCP, or Azure in minutes. These clusters take about 15 minutes to deploy, which is why you probably don't have time to start right now. Unfortunately, we can't make the cloud any faster, but we can make it a lot easier to actually configure it and deploy and manage the cluster. So let's go ahead and get started. So the objectives for today. One, I would hope that everybody's going to walk away with a basic understanding of the common Kubernetes terminologies and concepts, particularly with regard to running applications. Second, you should be familiar with the most common and most useful kubectl commands for checking on the health of applications and resources in your Kubernetes cluster. And last, you should be able to perform some simple diagnostics and troubleshooting of the common problems in when you're running applications. So before we get started, let's talk a little bit about some of the terminology that we're going to be using in this webinar. Now, there's a whole lot that can go into Kubernetes, but this kind of covers the main terms that we're going to be using. Kubectl, though I've heard people pronounce it kubectl or kubectl, this is the official CLI of Kubernetes. So this is what we're going to be using to check on the health of a lot of the stuff as we're running. The next one, Helm. Helm is just a package manager for Kubernetes. It's very, very common to see a lot of kind of prepackaged applications. Make it very easy for you to deploy, configure, modify, and even uninstall applications from your Kubernetes cluster. The next is namespace. In Kubernetes, a namespace, you can think of it as a virtual subcluster. for organizing your resources. You can kind of break your cluster into a bunch of smaller clusters, kind of with namespaces, and it's helpful for organization, but these namespaces also provide, I would say, a thin layer of security. A lot of Kubernetes permissions and RBAC can be limited around namespaces. And so namespaces are also a good way to provide some security around your resources and applications. A pod is a set of one or more containers that represents a single application instance. It's kind of one of the most fundamental and basic resources in a cluster. A deployment is going to be a logical wrapper around a set of pods. And the nice thing about this is the deployment can then provide some higher level capabilities on these pods. So, for example, a pod by itself, if it dies, it's just dead. But if the pod is being managed by a deployment and it dies, the deployment will see that and it will actually restart the pod. Similarly, if you're rolling out a new version of an application, the deployment is what will handle all of the teardown of all the old pods and the launching of all the new pods. So kind of the swapping of the versions, and whether it's a blue-green deploy or if you're just doing a rollout, it will handle that whole process for you. A service, this is kind of a bit of a less tangible resource. A service, you can think of it as just a logical grouping of pods. This is particularly useful for providing network access. Pods are ephemeral, and even within a deployment, the names are have a random suffix to them, and so that makes it very difficult to individually address pods. And nor would you really want to individually address pods. You want to address kind of the application as a whole, whether there's one pod or hundreds of them. You just want to say, I'm talking to that application. And the service allows you to abstract that and say, all of these applications are represented by this one service. And it also provides a single DNS name, which makes it a lot easier for you to then speak to all of those applications. So there's other uses for services, but that's one of the main ones. And the last term here is node. A node is just a Kubernetes worker machine. So just think of it as a VM instance that is running in your cluster that your containers can run on. Okay, so this is the last slide before we're going to get started and actually get in running commands and debugging applications. I know there's a lot. This is a kind of a cluttered slide, but I'm trying to get as much on here as I can. This is probably the single most important thing in this entire webinar. If you can learn what is on this slide, then to be honest, you can probably diagnose 90% or more of the application issues that you're going to run into. Just with these commands, and honestly, specifically just those first 3 commands are going to be crucial in debugging applications. So I could stop the webinar right here and just say, go learn these commands, but I'm not going to do that. I do think, though, it's important to point out that while Kubernetes is powerful and you could say complex and intimidating, a lot of that complexity is actually hidden behind some pretty safe defaults and some simple abstractions and simple tools. If you can debug and diagnose with just 3 commands and permutations of 3 commands, that shows that a lot of the complexity is actually pretty bounded. And this allows organizations to grow into Kubernetes at a pace that fits your needs. And so this is why I'm always an advocate for Kubernetes. It's very, very powerful, but you can take on that complexity only when you're ready. So I'm not going to spend the time to dig into each of these commands now. You're going to have plenty of examples to see how they are used throughout this webinar. And we'll actually come back to this page at the end, and we can recap then. So let's go ahead and get started. So if you remember, the first link I sent was a link to a GitHub repo. You should clone that repo locally and open up a terminal that is going to be in that repo. And so that's what I have right here. I'm in that repo with, and you're also going to want to open this in a editor. So I already have this open in VS Code right here, and I will be jumping back and forth between these two. So let's go back into the terminal, and the first thing that we're going to need to do is actually install all of these applications into our cluster. So I'm going to cd into the chart directory, and then I'm going to run a Helm command to actually install this into the cluster. So it'll be Helm upgrade debug. This is the release name. So whenever you're using Helm, you may want to use Helm to install multiple instances of the same application. And so the release name is what needs to be unique. And so we're just going to call this release debug. We're saying to use this dot means use the current chart, the one that's local. The -n debugging here says install it into the debugging namespace. So we're going to install all of this stuff in its own namespace so we can keep it isolated. -I means install it if it doesn't exist. And then the last one is create namespace. So this is a long command, but you can go ahead and enter. The nice thing here is that this command is completely idempotent. We can run it multiple times, and we are going to come back and run this command every time we make changes locally to try to fix things. So luckily it was just installed. It's running in the cluster. So let's check on everything. So we can use the first kubectl command. It's going to be kubectl get pods, and we're going to scope this to the debugging namespace. So there we go. What we're seeing here is all of the pods. That's what kubectl get pods did. It's showing us all of the pods that are in the debugging namespace. And what you can see is it's a bit of a bloodbath. Nothing here is running properly. We've got some pods that are crashing. We've got some errors. You can see there's an OOMKilled there. So we're going to just start working from the top down through the bottom and fixing every single one of these issues until every single one of them is running properly. So we're going to start with this top one right up here that is going into a CrashLoopBackOff. And actually, if I do kubectl get pod again, you might actually see it saying, there it is. Now it's saying a CrashLoopBackOff. Previously, it was an error state. It is restarted 3 times now. So let's talk about what is a CrashLoopBackOff. Like, what does this status even mean? So this means that the pod is starting to run. It's coming up. It's crashing, and then it's being restarted by Kubernetes, and it's continuing to do that. That's the crash loop. It's being started and crashing and started and crashing. The back off part means that Kubernetes will wait an increasing amount of time between each restart. And I think it maxes it at 5 minutes, but I believe that's configurable. It does that to prevent unnecessary thrashing. Instead of just crashing, starting, crashing, starting, crashing, starting, it will wait a little bit with the assumption of this isn't something that's just going to resolve itself. Like, you probably need to step in and fix it. The important thing to note here, though, is that the container is what's crashing. This means that it's probably not a Kubernetes issue. It's an issue with the Docker container, with what we're trying to actually run. So the next thing we can do is let's check on the logs in the container to see if we can get a hint as to why this container is crashing. So the next command that we're going to see is kubectl logs. Again, we're going to scope it to the debugging namespace. And with this command, you can either give it the name of the pod itself, which would be this. We could just put this in. We'll actually run that. The other thing you can do, which we'll see in the future, is you can use Kubernetes labels, which are key value pairs, to kind of filter and scope the command to exactly the ones that we want. We'll see that on the next time. So luckily, we have a very useful error here. The error is saying that the Postgres password must be set to a non-empty value. And so this is an environment variable. And so it means that we must have not set this environment variable. Let's jump into the editor and take a look at this deployment manifest to see if that is the case. So these are ordered in the same way that they should be in the terminal. So we look at the CrashLoopBackOff, and luckily I've kind of already put in and commented out what the fix is going to be here. It's just going to be adding an environment variable with, obviously you can see here, a very secure password. So let's just uncomment that. We're going to save this. So now this deployment is going to have that environment variable declared. Let's jump back over into our terminal, and we're just going to rerun that Helm upgrade command, because again, it's idempotent. We can rerun it, and it's going to reinstall with that updated deployment manifest. So it just ran. Let's check the pods again. And you'll see now it's actually up and running. It's not in a CrashLoopBackOff state, and it's not in an error state. So we've already fixed that one. And we use kubectl get, and we use kubectl logs to be able to diagnose what was wrong there. So let's move on to the next one. We got one down. We got 5 more to go. And maybe if we have some time, we'll get into, I have kind of an extra credit one. We'll see. So if we look at it, the next one that we have here is it's the failed readiness. So this one might look like it's okay. You can see that the status is running. It's a little bit subtle here. Notice that on the healthy pod under ready, it says 1 of 1, the one that we just fixed. In this one, it says 0 of 1. And this actually implies that the pod is not healthy. It's not ready. So what does ready mean? So in Kubernetes, ready means that it's ready to receive traffic, you could say. If this application was intended to be serving traffic, Kubernetes actually wouldn't be sending any to it. So, and if this was the only pod, effectively your service would be down. It would not be serving any traffic at all. So the next question is, well, how does Kubernetes determine whether or not a pod is ready? Well, by default, it's just if the container is running. If the container is running, then Kubernetes is going to say that it's ready. However, just because a container is running, that doesn't mean that it actually is necessarily ready to serve traffic. So, for example, your web application might need to warm a cache or perform some startup checks. You might need to load an ML model. Who knows? You might have some internal things that you need to check on or do before your pod's actually ready to serve traffic. Kubernetes actually allows you to specify different types of readiness checks. They can be HTTP checks. They can be little scripts that it will run in the pod to determine. There's a few different ways to do it. We're not going to dig all the way into what these readiness checks are and exactly how to configure them. The main thing here is we need to see that it's not ready and be able to diagnose and fix that. So the fact that it's not ready, even though it's running, implies that we must have a defined readiness check that is failing. So the next thing we're going to do here is use the third command of those top 3, which is describe. So let's describe this pod. We're going to do kubectl describe. And this is where we could, again, copy and paste this pod name. But instead, we're going to use the label filters to get it. So we're going to say, in the namespace debugging, get or describe all pods that have the app label equals failed readiness. And there's only going to be one pod, and it's going to be this one. So describe is going to give us some status information about it. There'll be some thin configuration, which you see up here, but the really useful stuff oftentimes is down here in events. This is going to show us all the events that are relevant to this pod in the last, I believe it's hour by default. And so you'll see here, we have a readiness probe that is failing, and it's failing with status code 404. Which, if you guys are familiar at all with HTTP status codes, 404 is not found. So this probably means we have an HTTP that's pointed to a bad endpoint. So let's jump over to our terminal and take a look. So we're done with this CrashLoopBackOff. Let's open the failed readiness and check on the deployment. And under this readiness probe at line 20, you'll see we're telling it to do an HTTP get on a path that is /not-real endpoint. And what do you know? That actually is not a real endpoint. And so you can either comment or delete this line. I'm just going to comment it out, and I'm going to uncomment the line beneath. Now, I would recommend most of the time you should have a dedicated health endpoint like /health. I've also seen /healthz. In this case, we're just running Nginx. And so if Nginx is serving traffic, it's ready to go. And so we can just use the kind of the default just /endpoint to determine the health. So let's save that. We're going to jump back into the terminal, and let's run Helm upgrade again. Take a couple of seconds, and then let's run the kubectl get pods. And hopefully here we're going to see this failed ready come to a 1 of 1 status. And actually, you can see there, it took a couple seconds and it tore down. You'll see previously we had 2 of them up. We had the old one that was up for 8 minutes and this new one. And as soon as this new one made it to ready, 1 of 1, it actually tore down the old one. So we even got to see how Kubernetes does that. It brings up the new one. When the new one gets ready, it tears down the old one. So we're now done with 2. We fixed 2 issues. In this one, we used kubectl get and kubectl describe to be able to determine what was wrong there. So let's jump into the next one. This one's going to be an image pull back off. You can see right here. So we already kind of know what the back off means, right? Exponential back off. The image pull part is basically implying that Kubernetes is unable to pull the proper image for this application. So whatever image we've told it to run, it can't. This could be for a few different reasons. It could be that there's a network connectivity issue. It can't reach the container registry that you specified. It could be that you specified a private image and you haven't specified the credentials necessary, or you've given improper credentials, and so it can't valid or it can't authenticate and pull the image. It could just be a good old-fashioned fat finger of the image name, and you misspelled it, and so it can't find that image because it doesn't exist. Let's check on the deployment manifest and see if we can figure out what's going on with this thing. So I'm actually going to show a little variation on the kubectl get command. So we're going to do kubectl get pod. Let's just copy paste the name of this one. We'll just copy paste it and put it in there. We're going to say in the debugging namespace, and we're going to say this time -o YAML. This means output it in YAML. So instead of us just giving like the list of them here, it's going to give us the full YAML dump of what the manifest is that's running. And so you can see we can scroll up, and if we look under containers, we can see the image name here does not look right. In fact, it looks like it's Nginx spelled backwards, which is kind of, I suppose, a bit of a clever thing. We did not mean to run a backwards Nginx. In fact, this doesn't even exist as an image, and this is why we're having issues pulling the image itself. So let's jump over into the terminal. Let's go into the image pull back off, into the deployment. And once again, let's comment out the bad one, and let's uncomment the good one. Let's save it. Back into the terminal, and let's run Helm upgrade and update it. Now, hopefully, this is going to fix it. So let's do a kubectl get pods. And there we go. It is up and running. So look at that. We've already fixed 3 of them. We've got 3 more to go, and then maybe extra credit. So this next one is in a CrashLoopBackOff, but secretly I know what's wrong, and there's a bit of a timing issue of whether or not it's going to display the real culprit here, which is that it's OOMKilled. You may have seen that, I think, early on. If we scroll all the way up in the terminal, we may have seen an OOMKilled status. Perhaps not. No, right here, OOMKilled. We had on this one. So one way that we can do it, so let's say that you didn't see that and you didn't know that it was OOMKilled. One of the things that you can do is just run a kubectl describe, which is what we're going to do here on this pod. Actually, sorry, I need to put pod here. You tell it what resource to describe in the debugging namespace. And you can see down here in the event, it's saying it's backing off this, restarting the container. If you scroll up just a little bit, you'll see here the last state was terminated and the reason was OOMKilled. And so if you're not seeing it just when you're doing a kubectl get, you can also always check up here, and this will give you the reason for why the pod was last terminated. If you are unable to see that just when you're doing the kubectl get. So let's briefly talk about what does OOMKilled even mean. So this is actually going to lead us to a broader discussion about resources in general, because OOM means out of memory. So this pod was killed because it ran out of memory. This issue specifically arises when a pod or a container specifically attempts to acquire more memory than it's allowed to. And so we need to talk a little bit about how resources even work in Kubernetes. In Kubernetes, these pods are intended to be ephemeral. That's the idea of cattle, not pets. At any point, your pod should be able to be terminated, moved, and restarted with zero or minimal impact on the overall application. However, in order for Kubernetes to schedule your pod, which basically means placing it on a node, Kubernetes needs to know some things about this pod. One of the most important ones being how many resources in terms of CPU and memory does this pod need? So when you're defining your containers in the Kubernetes pod, you can actually specify two levels of resource allocation. One is requests, how many resources this pod or container requests, and what are the limits. Let's start with requests. Requests are going to be your way of telling Kubernetes this is how many resources one instance of this pod is expected to consume. And it really should be your best estimate at the expected resource utilization of the containers. When Kubernetes is attempting to schedule your pod, it's going to look through the nodes and it's going to try to find a node with enough spare capacity in terms of resources, CPU and memory, for your pod. So how does Kubernetes know how much capacity remains? Well, it's not by checking the actual CPU utilization and memory utilization on the node. It doesn't go and look and see what the CPU load is. For one, this can change second to second. You can have a burst that will, consume a whole lot. You can also have it idling, and the node could look effectively empty, even though it's mostly full. So the way Kubernetes knows how full a node is in terms of resources is actually by summing up all of the resource requests of the pods that are currently running on there. And so it has nothing to do with the load. It has everything to do with what else is scheduled here. And this is another reason why it's so important to specify your resource requests. One, you're telling Kubernetes how much your container needs. This lets Kubernetes know and how to find a node that has enough spare capacity, but also it informs Kubernetes how much capacity on the node, once it is placed, needs to be reserved for it so that it doesn't get consumed by other nodes. This is, again, a reason why it's so important to be accurate here, because if you give too much headroom, you're going to be, your cluster is going to be very over provisioned. You're going to have way more compute than you need because everything is over provisioned. Additionally, you shouldn't under provision because you can really run into resource constraints on your pods. If you say it only needs half a CPU and it starts using a full CPU, you're going to start eating into resources, of other potential workloads. Now, this is also where the other side, resource limits, can come in. So resource limits are going to be hard limits on the resources that this pod can use. So if you put a limit on the CPU, Kubernetes, and actually it relies on Linux C groups, but it will throttle the CPU. So if in that situation, if you said, I'm requesting one CPU and I'm also limiting it to one CPU, if your application tried to use more than one CPU, it would get throttled. The Linux kernel wouldn't allow it to use any more CPU than that. And so that's not a huge deal, but when you start putting memory limits on, it actually does become a big deal because you can't throttle memory. What ends up happening is as soon as your pod tries to request more memory, it's immediately going to get killed. And so this is what happens with OOMKilled. And again, this is the reason why limits should be used, I would say, very perhaps sparingly and very intentionally when you're putting them on pods. You should always give headroom on the limit. It should be above standard operating levels for this pod, and you should probably be putting it in just to safeguard like one pod just consuming, requesting one CPU and using 10. Right, that's the main reason why you'd use a limit, is to make sure you don't have runaway resource utilization. So let's check on this pod configuration to see what the memory limit is that we've specified. So let's do that same command, kubectl get pod. In this case, let's just use the app filtering. We're going to do in the namespace debugging, and we're going to say for the pod where the app label is OOMKilled, and its output the YAML manifest here. And if we scroll up and we look at the resources, you can see we're requesting 500 CPU, half a CPU, and we're limiting it to 1/10 of a CPU. And we're limiting we have a hard memory limit of just 10 megabytes. Now, I can tell you, I wrote this application. It's just a little Python app, and it needs more than 10 megabytes to be able to run. In fact, it needs about 50. So let's jump over into the manifest for OOMKilled. And you'll see in here, once again, we have a hard limit on the memory of 10. That's a general rule of thumb, is your limit should be at least 1.5, if not 2 times what your what your request is, what your expected usage should be. So let's bump it up to twice. What that is, again, it should be using about 50. So let's put the limit to 100. Let's save, and let's redeploy this. And let's get the pods again, and hopefully we're going to see it's up and running. There we go. It's been running for 4 seconds, and it is going to continue running healthy now. So that's 4 now. We've got 2 more to go. And we're actually, looks like we're doing all right on time, so we might have time for the extra credit, I will say. So let's look at the next one. It is stuck in a pending state here. So instead of running, it's stuck in pending. So what does pending mean? So this means that the Kubernetes scheduler can't find an appropriate node to place the pod on. There could be a lot of different reasons for this. We can use kubectl describe actually to hopefully give us some hints as to perhaps why it can't find anywhere to schedule it. So let's describe this pod right here. We do kubectl describe on, and we'll put that in there. And again, we scope it to the debugging namespace. That's where it's running. And we have right here, we actually have 2 of them, and both of them are relevant. 2 events here. One is the failed scheduling, the lower one. Let's read this one first. It's saying 0 of 3 nodes are available. So this implies there's 3 nodes, but none of them are available to be scheduled. It says 3 of them have insufficient CPU. Preemption, by the way, preemption means sometimes if you have a high priority node, Kubernetes will allow you to, it can actually evict lower priority like workloads to allow you to place high priority workloads. Very clever. And this is kind of one of those advanced things you can do that allows you to really customize and tailor Kubernetes. So, if you're in a situation where you're resource constrained for some reason, Kubernetes you can tell it how to identify your low priority workloads and evict them to make sure your high priority workloads are running. But that's not particularly relevant to this situation, but that's just what it's telling you, is that there's no preemption available to solve this either. The last thing is we're seeing the cluster autoscaler also saying that this pod didn't trigger a scale up because of insufficient CPU. So all these alarm bells right now look to be complaining about the CPU. So if we look right up here, we can see the resource requests here. And this is probably why we have requested 20 CPUs for this workload. That's a lot. In fact, that's probably more than any of the nodes have. So let's take a look at our nodes. So we can use kubectl get nodes. And we don't have to put namespace on this because nodes aren't bound to a namespace. Only certain resources, specifically like applications and things like that, pods, services, are bound to a namespace. Nodes are at a cluster level. So you can do kubectl get nodes. You can see there's 3 of them here. Let's describe one of these nodes. So kubectl describe node, and we'll put that node in. And if you scroll up here under the capacity section right here, this is going to tell us how many CPUs are actually available on the node. And so you can see the capacity is only 2 CPUs. So each of these nodes only has 2 CPUs available. So this is also why Kubernetes didn't trigger a scale up. So this is where Kubernetes is smart. It says that this thing asks for 20 CPUs, but that has to be, you could say, atomic. It has to be all on one node. It's not going to try spinning up 10 new nodes, which are all 2 CPU each, and be like, well, there's 20 CPUs available in the cluster now. The pod still can't land across 10 nodes. It has to land on a single node. And there's no way we can't add, if we added a new node, we would just be adding 2 CPUs. And therefore the autoscaler said, I can't help out. If I scaled up, it still wouldn't solve this problem. So this autoscaler is actually still saving us money here by not, attempting to solve a problem that it can't solve. So the main issue is we're asking for 20. We only have 2 available. So this is where, again, this whole resource request thing comes in that we just talked about earlier. We could lower the resource request on this down to 2 CPU, but the other thing to keep in mind is there are workloads called daemon sets. And daemon sets are going to be workloads that run on every single node. So instead of saying, I want this application to have 5, replicas running, in a daemon set, you don't specify the number of replicas. It's implied. It is 1 per node. And actually, if we look at the pods that are running on this, I can just tell you which ones I know happen to be daemon sets. This AWS node is I believe the CSI node is a kubeproxy, I believe is. And so if you look at this, they're already eating into that 2 CPU, the 2 CPUs that are available. So really, we actually only have about 1.8 or 1.9 CPUs actually available on any of the pods, because some of those resources are just going to get chewed up by the daemon sets that are going to get landed and scheduled on it. So that's something to keep in mind. If you have nodes that are running 2 CPUs, that doesn't mean you can run workloads that are 2 CPU. It probably means you can run, I would say maximum 1.8, but probably more likely 1.5. So let's jump into the actual deployment manifest. And update this to give it a bit more reasonable resource request. So instead of 20 CPUs, we're just running Nginx. Nginx only needs a 1/10 of a CPU here. So let's update it to that. Let's save. We're going to run Helm upgrade again. And if we do kubectl get pods, hopefully we see, there it is. It's up and running, 1 of 1. So there we go. It is resolved. So we've now done 5 of them, not including the extra credit. We got 1 more to go, and I think we're doing all right on time here. Good deal. So the next one that we're going to go into is actually also stuck in pending. So we're going to there's lots of ways that pods can get stuck in pending. Obviously, this isn't going to be exhaustive, but we've seen it due to resources. We're going to have to dig in and figure out, so why is this one stuck in a pending state? So as we did last time, let's do a kubectl describe and see if describe can give us some hints. So kubectl describe pod. And by the way, a lot of these have acronyms. PO is pod. So we could do a PO. This one in the debugging namespace. And let's take a look at the events. And under failed scheduling, we have 3 pods, or 0 of 3 nodes are available. And all 3 of them, the pod has unbound immediate persistent volume claims. Once again, preemption isn't eligible. And once again, the autoscaler saying there's nothing I can do here to scale up and solve this problem. So, and this makes sense if you understand what a persistent volume claim is. So you may have actually noticed if I do a kubectl get that this pod has a slightly different naming convention. It just has a 0 here instead of these kind of random suffixes. That's because what we're running in this case is not actually a deployment. What we're running is a stateful set. A stateful set in Kubernetes is going to be generally is going to be backed by persistent storage. It's going to have state associated with it. And that state is generally going to be by way of a persistent volume claim. This is just Kubernetes' way of representing persistent storage in a, you could say, a runtime or in a platform, and speaking about Kubernetes, where your application can get scheduled on any arbitrary node. I mean, think about this problem. Your pod could get killed on, node A and get scheduled on node C, but you have persistent volumes that need to move with it. You have data that needs to move with it. And this is what a persistent volume claim does, is you make a claim against storage, and then the idea is the storage needs to be able to move when your workload moves. And so what it's saying right now, the reason why it's complaining is it's saying, I can't bind your persistent volume to any of the nodes. And so this is really, it's an issue with, we can't get the storage that is backing this workload. That's what it's complaining about right here. So the best way for us to figure out why is let's dig in and look at this persistent volume claim to see if we can figure out what's wrong with it. So if we do kubectl get PVC in the debugging namespace, you'll see that there should just be this one. Yeah, and Kubernetes does some creative things with the naming convention here. But you'll see it is stuck in the pending state, this persistent volume. So let's do describe to see if, we're not getting a lot from this get. We're just saying that it's stuck in pending. Let's run kubectl describe, since that can give us maybe some event and scheduling information about what's wrong. So let's describe this PVC. We can put the name in the debugging namespace. And if we see under events, we've got a warning right here that's saying the provisioning failed. And the message is actually very useful. It's saying the storage class, not real SC, this should give you a hint, is not found. So what this is talking about is a storage class. A storage class is just a way of dynamically provisioning storage for workloads, if you'd like to. I don't really have time to probably dig into exactly, all the differences between persistent volumes, persistent volume claims, storage classes, and all that. But just simply know that it's a way to represent and dynamically provision storage for your workloads. And so what it's complaining about here is saying you're asking for a storage class that I can't find. And so we can actually see what are the eligible storage classes. We can do kubectl get storage class. You'll see we have exactly one, and it is not called not real SC. It's actually called GP2. In AWS, GP2 means general purpose 2, and it actually just represents an EBS volume. And so we're trying to use a storage class that is not even real, and that's the reason why this is failing. So let's jump back into the editor, and let's update the storage class to be something that's actually real. So we'll close this one. We'll jump into the pending volume, jump into the stateful set, and you'll see here on line 35, we can just comment out the improper storage class and save it with the eligible one, the GP2. So let's go ahead and, did I save that? I don't know if I saved that. I did. Let's jump over and let's try redeploying this. Whoopsie, sorry, I believe I shifted my camera a little bit. There we go. So let's do, let's run Helm upgrade. What we're going to actually see here is we got an error, a failure. This isn't good. So let's see what it's complaining about here. It said cannot patch this stateful set. And the reason is because the field that we're trying to update is forbidden. It's saying only updates to the replicas, pod template, or update strategy, the retention policy, or the min ready seconds. Updating anything besides those fields is forbidden. If you step back and think about it, this actually makes sense. We just changed the storage backing of this application. Let's assume for a moment, or let's think for a moment, what if this thing was actually running? What if this was a database? What if this database was using a actual valid storage backend? What if we were using GP2 and we were trying to move to GP3? And Kubernetes just accepted and was like, all right, dude, let's move to, from GP2 to GP3. Kubernetes doesn't have a way to migrate all of your data, from one volume type to the other. Like, this is an entirely new volume. And so this is, in some sense, a potentially very destructive and disruptive change. And so Kubernetes is halting you from doing something that would actually be probably very catastrophic. It's saying you can't change that field dynamically. So, however, we know this thing hasn't even come up and run properly. So what we can do is we can delete it, and we can then redeploy it in this proper state, and it'll come up properly. So we're going to do kubectl. We're going to delete that stateful set, in the debugging namespace, and we're going to do the using the app label app equals pending volume, and we see that it just got deleted. There's also a delete that persistent volume claim that was in there. We can use the exact same command, except we'll do PVC instead of stateful set. There we go. Those are both deleted. Now let's try running that same Helm upgrade command, and hopefully this time it's going to work. And if we do kubectl get pods, it looks like the container is creating. It's probably just taking a few seconds to provision the volume, and there it is. We run it again, and it's up and running. And if we check on the PVC here, not delete PVC, where's get PVC? We'll see that it's bound, it's provisioned, it has capacity, it's the GP2 storage class, everything's good. We now have actually a stateful workload running. There's storage that is backing this thing. So we're good. So that's 6 out of 6. How are we doing on time? We got 14 minutes. Okay, I think we can move through this next one. We'll have to go fast. I know we've been going fast, but I wanted to get through as much of this as we could. The last one is actually debugging web access. So I have an application here that actually should be available if we jump back over in this window and I refresh. There we go. We've got an application. It's running at webinar.mdawssbx.com. And we're getting a 503 temporarily unavailable. And so this thing should be up and serving traffic. It's actually just an Nginx pod. So we should be getting that Nginx homepage, right? Welcome to Nginx. So let's figure out and see if we can fix what's going wrong here. So we're going to jump back into the terminal. And we're going to, well, the first thing is we can immediately see the same issue that we were having earlier of that this thing isn't ready. And if you remember, pods are not going to receive any traffic if they aren't ready. So that has to get solved first and foremost. So let's do a kubectl describe on this thing to see if we can figure out why it's failing its readiness check. So we'll do describe pod, this one in the debugging namespace. And there we go. Readiness probe failed. In this case, we're having connection refused. If you remember last time, it was 404, and that was because it was an invalid endpoint. 404 means, path not found. In this case, we're getting connection refused. This generally means like your pod is not listening. Like there's nothing listening to where it's trying to connect. So let's take a look at the actual manifest and see if we can see what's wrong. In web access, let's open the deployment.yaml. And if we look here at the container, the Nginx container, we have a port open and declared. That's what this is right here. We're saying the port is port 80, yet when we're setting up the readiness probe, we're setting it to 81. So this would be why we would be getting a connection refused. It's because the port that is open is not the port that we're checking for the readiness check. So we could set this just to port 80. However, Kubernetes actually has a clever way that you can name your port, which we did right here. We named it HTTP. And then instead of specifying the port number, which now has to be synced, we can actually just say, hey, use the port that's named HTTP. And now this is nice. We can, if we change this to, for example, port 8080, it would get updated everywhere that it's referenced by name. So instead of having to then update 8080 everywhere, we don't have to update it. We only update it in one spot right here, as long as we use the name elsewhere. So let's save that. Jump back into the terminal. We're going to redeploy. And hopefully we're going to see this pod now go into the into a ready state. There we go, and it is. It's 1 of 1. It should be receiving traffic now. So let's jump back over to the web page. Let's refresh, and it's still not working. It's still 503, service unavailable. So something's still wrong. So let's open back up the terminal. We're going to now use one of, I think, the most powerful tools, particularly when you're looking at debugging web applications, and that is the port forward command. What port forward allows you to do is you're able to take a remote port in Kubernetes on a container, and you're able to bind it to a local port on your system. And then you're able to talk with your local system, and it's going to be forwarded to the Kubernetes cluster. So this allows you to do some testing against the pod itself. So let's run it. Let's run the command. It's kubectl port forward, and you can actually do it to pods or services. We're going to do it to the pod right now, and we're going to copy this pod name in. And you notice I'm doing pod / I believe you can also just do pod space. Let's see if this works. I believe this right here works. We're going to do in the debugging namespace. We always have to scope these things to the namespace. And then this last one is going to be the port. Now, we could just say 80, and it will, if we just specify one value here, 80, it's going to do both 80 locally and 80 remotely. But a lot of times 80 is kind of a blessed port on your local system, so you don't really want to conflict with it. So instead, we're going to say locally use 8080 and remotely use port 80. And so this will make sure we're in kind of the ephemeral port range, or we're outside the standard port range, so we shouldn't have any port conflicts. Now, if we run this, you're going to see, whoopsie, pods. It must be that we can't do that. So let's just do pod /. There we go. That time it worked. And you'll see it's saying we're forwarding our local port 8080 to the remote port just 80. Now you'll also see this is taking over this terminal. And so we're going to just open up another terminal here really quick. Let me make this bigger for you guys. And we're going to do curl localhost 8080. And the good news is what we're seeing, we're getting a response, and it's a bit hard to see, but this is the HTML response of Nginx. This is a very good sign. So this means the pod is actually running and serving traffic well. We know what Nginx looks like. This obviously would be tailored to whatever it is, the application that you're running. You want to see that return here. So we know the pod's healthy. So now we just need to move up the stack. So in this cluster, the way that this is working, there's a lot of assumptions that are built in here. One is that we have the Kubernetes cluster, and it is running, and we have some degree of confidence that it should be serving traffic. And in this case, serving traffic is via a ingress controller. We're actually just using the standard Nginx ingress controller, the default one that Kubernetes has. So the way that it works is traffic is going to come in. It's going to go through the ingress controller, assuming you're using ingress. It's then going to get routed to a service, and that service is going to then send it to one of the pods. And so what we're going to do is we're going to work our way up that stack. We just checked, and we know the pod is working just fine. So now we need to move up to the service and figure out if the service is working. So let's check on the service and see if the service is okay. So if we do kubectl get service in the debugging namespace, SVC is shorthand for service, by the way. You'll see there's this web access one. This is the one that we care about. So let's kubectl describe that to see if we can get some useful information about this service. And the main thing that I want to point out here, again, I'm rushing through it. I'm not showing all the stuff that we could look at just because we're constrained with time. But endpoints here is the really important thing whenever you're checking on a service. This endpoints list, this is going to be a list of pods which are, it's going to look like IPs which are effectively being managed or mapped by this service. And so the fact that this is empty means that something's wrong. This service can't find any pods to send things to. So let's jump over into the service configuration, the service manifest, and see if there's any hint as to why. And as usual, I've commented out the actual fix. And what's going on here is services have this concept called selector. And actually, this selector pattern shows up throughout Kubernetes. What this selector is for is it's basically the service saying, how do I select which pods I should be directing traffic to? Because you may have a pretty large and complex application that could have multiple different types of pods running behind it. And you don't want to send traffic to all of them. You may only want to send traffic to a subset of them. And you do that via the selector. And the selector is going to be a list of labels, key values that all have to match. It's not an or, it's an and across all of these. And the main issue is this should not be hyphenated. And so let's comment out this one. We'll re-add this one. And by the way, so what I'll do real quick is if I jump over here, for example, and I do kubectl get pods in the debugging namespace, where the app label equals, what was it, web-access, you'll see this is going to come up as empty. There's no pods. And this is what the service has been doing, trying to find pods. However, if I remove that hyphen, suddenly I'll get that one pod that I want to send traffic to. And so that's the exact same thing the service is going to do to find it. And so that's how this is going to work. So I've already made the fix. I've saved it. If we now do the Helm upgrade, it should get that service working. And actually, if we now do that kubectl describe that service, we should see now, there it is. It's got an endpoint. So now the service is working as well. So let's jump back in or over to the web page. Let's refresh and let's see if that works. And it doesn't. So we fixed the pod. We know the pod's working. We fixed the service. We know the service is working. The last thing is going to be the ingress itself. And the ingress is going to be the thing that says what domain, like webinar, where should it be hosted, and how should I route to the proper service. And we're coming up a little short on time here, so I'm going to jump straight into the ingress itself. And you'll see here that once again, we've fat-fingered the port on the service. And so let's comment out the port number, and let's instead use a port name of HTTP here, which again kind of advocates for why you should always use the name if you can, instead of the actual port number when you're referencing the port. So we'll save that. We'll jump over into the terminal. Let's run Helm upgrade again. And it's out. Now let's jump over and let's see if this works. If we refresh the page, and that's exactly what we're looking for. Nginx is now serving traffic properly. So there we go. That's the last one. I suppose the extra credit. So let's jump back over into the slides. That was everything. That was 7 different scenarios that we just went through. And you'll notice we got through all of them. We didn't even use kubectl exec. We got through and diagnosed every single one of those issues just with 4 commands. And that really shows you if you learn those 4 commands, you can debug, diagnose just about everything that you need, that you're going to need to in a Kubernetes cluster. So as a recap, we fixed a CrashLoopBackOff. We fixed an image pullback off by fixing the image name. We learned how readiness checks work. We learned how that can resource limits can affect things like OOMKilled and how to fix them. We learned how resources are used to place pods and how to fix pending pods due to resource issues. We also figured out how volumes can cause pending issues. and we fixed a pod that wasn't web accessible, and we made it web accessible. The last thing I'd actually like to show really quick before we end this webinar is if you take a look at our platform, MassDriver, we actually help you both run Kubernetes and understand the health. So you'll see we actually have health metrics coming through for your cluster. And so a lot of the things that we actually went through, like checking the ready status of your pods, whether they're crash looping, if the last rollout of them was successful, we check on all those things for you, including if your autoscaler is at the max size. We do this at the cluster level, but we also do it at the individual application level. This is an application running in. So we're trying to make it even easier for you to be able to understand the health of all of the things that are running in your Kubernetes cluster. So head to massdriver.cloud to take a look at it today. And that is all. I'm going to stick around for a few more minutes in case there are any questions that anybody has. You can ask in the comments. But otherwise, thank you for sticking through this whole thing. I hope it was useful. And head to massdriver.cloud to check it out and get started today.